Okay, so welcome everybody to our Gamma seminar. Today we have the pleasure to guest Rubén Izquierdo from IFEMAT, who is going to talk about the graded Jacobi bracket in dissipative field theories. So Rubén, thank you for accepting our invitation. It's a pleasure to have you here. The floor is yours.
Thank you very much for the invitation and for giving me the opportunity of presenting this work. This is a joint work with two people who are in the audience right now, which are Manuel de León and Xavier Rivas. This was actually done, well, it's gonna be a year now, although this work probably will be published soon enough. I will give you the reference in a minute. I'm going to present just a generalization of the Jacobi bracket, but in the case of multi-contact field theories, or not necessarily mechanics, but for more general Lagrangians dependent on several variables. So this is, oops, sorry. Okay, now this is going to be the plan of the talk, which I have divided in four sections. The first one is just going to give a little motivation on the Herklotz variational principle and such. Then I'm going to go into what we did in the work, which is to define conformal symmetries and Jacobi brackets, both all in a graded sense, which I think it's the interesting part of the work, to understand multivectors as conformal symmetries and the associated forms as possible things to measure and this sort of stuff, although this probably will be part of a future work. And then I'm going to talk about the process of pre-multisymplectization in general, which is really just an analog of when you get a contact structure, you may associate to it a symplectization, of if you have more generally, I will say, a contact distribution, you can still assign to it a symplectization, etc. And how this induces a notion of multi-contact structure. I will try to compare with some previous notions in the literature. So specifically, Luca Vitagliano's notion of multi-contact and K-contact manifolds, K-contact geometry, which I know people here are working. And finally, I will try to describe how to write dynamics and what does this graded algebra of Jacobi brackets says to us. And it's just going to be, say, a graded algebra of dissipation laws or dissipated forms. Okay, this is just what I just explained. Please keep in mind the first section is not going to be exhaustive at all. I'm going to go past most of the details, and it's just going to be very, very introductory, let's say. And then the second ones, I will give more detail here. The second one, this will be done for a general differential form, not necessarily one that we will call multi-contact. Then we will introduce the notion of contact in the third, and the fourth, I will explain why I already told you. Great. So this is based on this work. So brackets in multi-contact geometry and multisymplectization, which is going to appear soon enough in Mediterranean Journal of Mathematics. Although some points and motivations are part of a different ongoing work, so mainly the non-cooriented point of view, and also a bit of the extension of the work on dynamics that we did in this article, which is really to include say the reduced point of view on the multi-contact setting. Okay, so I'm going to start explaining things now. Please, if you have any doubt at any moment, please interrupt me. Great. So where does this sort of geometry come from? It comes from action-dependent variational principle, which is called the Herklotz variational principle. And as I said, this is going to be very much not in detail. And if you want more details, I would refer you to these articles, which are they explain very well the action-dependent field theory from the multi-contact point of view. There you can do as well things from the K-contact point of view or the K-co-contact point of view. But really what this talk is going to be about is from the, let's say, more covariant seeing it as the fiber bundle setting. And I would refer, and these are very nice references to look at. Okay, so suppose I have a fiber bundle, which I will denote y over x. Well, this might not be a fiber bundle. We can ask only a fibered manifold. And n will denote always the dimension of x. Maybe I have not explicitly written here, but this is the case. So if I have some fibered coordinates, so x mu, fibers on the base, and yi are the fibers on the, well, the coordinates on the fibers, and I have certain Lagrangian, which this is going to be action dependent. So a first order Lagrangian, which is action dependent, that means it depends on the positions, it depends on the fields, on the first derivative of the fields, and then an additional variable, which these are the S mu, which represents, say, the action density. Okay. In what sense does these variables represent the action density? Well, in the sense that they satisfy these particular partial differential equations. So the divergence of these S mu's should be exactly equal to the Lagrangian. When you integrate this Lagrangian or the Lagrangian density over your base manifold in order to obtain the action principal, by employing the Stokes theorem or the Gauss divergence theorem, with this vector field, you may write the integral as the integral on the boundary of dS's, so of this term. So in this precise sense is what we mean that this Lagrangian is action dependent, in the sense that these S mu's via this particular partial differential equations represent the action. Okay, sorry.
Sorry, one stupid thing, Rubén.
Yeah.
You are talking about the divergence, yeah? So what you are assuming that you are fixing a volume form or whatever? Or
No, this is going to be just local.
comment or locally? Yeah? Okay.
Locally. This
Okay.
I'm going to, of course, this is just the exterior differential, right? I'm going to give this more local description. Sorry, this global description in a moment.
Okay. It's well, differential is not exactly, but anyhow. Oh, okay. I will let's wait for that.
Yeah. No, this is more the local picture. That's it. There is some details regarding boundaries, etc., that I have also not explained here. But well, this if you want more details, I will refer you to the other articles. Great. Okay. So, and this induces the variational principle, which is, okay, of all possible fields, I'm going to look for those that minimizes this particular functional, where these S's solve these partial differential equations. Okay. So, what are the equations that we get? The equations that we get are the Herklotz-Euler-Lagrange equations, which are precisely these ones. So, if a pair y of possible functions yi and s of x satisfies the previous variational principle, or solve more than satisfy, solve the previous variational principle, so they make a stationary, this particular action functional, then they solve this PDE, right? So of course I have this condition, but this is just really a defining part of the equations, but I have this part, right? This is a generalization of the usual Euler-Lagrange equations, but here I have the dependence of the action of the Lagrangian, which measures the, say, dissipative.
Rubén, sorry, you didn't say that X is orientable, yeah? The manifold X.
Sorry, yes. X is orientable. Not necessarily oriented, right? Rather, not necessarily with a fixed volume form, but it is oriented. Yes. I'm sorry. Okay. Otherwise, the integration is not, unless we go with densities or whatever, but just imagine X to be oriented. Great. Okay. So intrinsically, so let's coordinate dependently. This is what we're doing. We're going to the jet bundle. We are making the product with n-1 forms over X. And then an action-dependent Lagrangian is just a fiber map from this manifold to the top forms on X, right? So here I have natural coordinates, which are precisely the coordinates I had in the previous slides, and then the Lagrangian reads precisely as it read before. And with this global description, then I have more of an intrinsic point of view, which is that really of all sections, I'm going to look for those that make stationary this particular integral, where S, as Javi mentioned earlier, is now a form, and the divergence is really the exterior differential, and I impose the condition of the exterior differential on ds to be the Lagrangian. Okay, So if I can write the variational principle in an intrinsic way, I would like to have an intrinsic description of the equations of motion. And as in the case of the multisymplectic field theories, I will look for it via a differential form. So this form is precisely the multi-contact form. It takes this expression. It takes this local expression, and this can be used to describe, give an intrinsic description of the equations and compute symmetries, dissipated quantities, etc., etc.
Sorry, Rubén, can you explain intrinsically how it should be the multi-contact form? Why it should be this way, this manner?
Why it should be this way?
Yeah.
I mean, in the case of first-order field theories, this is just really, this part here. This part here is the usual Poincaré-Cartan form, although now fiber with respect to the S.
Mm-hmm.
And sorry, this one here, this one. This one is the usual Poincaré-Cartan form, the part on the right, and this one is the canonical form on this manifold here. And then you add these two, and you get this. Why should you add this? Well, first of all, the second part measures, say, the variational nature of the equations, and adding this first one imposes this condition.
Okay, thank you.
Imposes this condition. Maybe I have murdered the explanation. Probably you can get a better explanation in the articles I cited.
Yeah, sure. It's just a general idea for those who have not seen this.
Yeah, okay.
It's okay. Okay, thank you. Okay. I know that you will not deal with this with detail. You are focusing on the second of the following part. Thank you.
Yeah, thanks for the question. Okay. So then this can be used to give an intrinsic description of the equations. However, this description is rather involved, as I will try to explain now. Particularly, there is a particular one form, which is called the dissipation one form, which is defined as such. So it's the unique, when it exists, which is not always, is the unique one form that satisfies this particular equation. So the wedge product with the contraction with a particular family of vector fields on the theta, it's precisely the contraction of these vector fields with the differential of the theta, right? This one form is something which, from my point of view, complicates a little bit how to study this sort of stuff, and it does not always exist. You cannot pose a particular. There are some. Say degenerate Lagrangians for which this is not really a thing you can define. However, when it does exist, it takes this local expression. So it's really the partials of the Lagrangian with respect to the axion variables, and it measures the dissipative nature of the equation. So this will just give how dissipative is the equation in each particular direction of the x. And when it does exist, the equations are written as such. So this is precisely the condition of differential of S equals to the Lagrangian, and then this one measures the conditions, the more differential condition on the the equations. Okay, and then in the previous really a multi-contact structure was a structure in such a way that it recovered this local case. Great. However, this motivates us, and this is like from now on, really, it's the start of the talk. This motivates us to at least introduce a more general notion of multi-contact structure, maybe to allow for a more flexible treatment of restrictions, quotient, etc. In particular, we would like to define the dissipation one form in a more geometric way, not so dependent on the linear type. So on the particular expression of the differential form, and then maybe obtain this as a corollary. And then, as the title of the talk says, I would like to define a graded version of the Jacobi bracket, studying its properties, and then come back. So I have my problem, I make the generalization, I start doing my mathematical stuff on the generalization, and finally I would like to come back to the case of field theory, see what I have learned. Good. Okay. So now I'm going to forget about.
Sorry, Rubén.
Yeah.
A last question. Just a small one. When you have an ordinary differential equations, you know what dissipation means. Yeah, it's pretty much clear. But in field theory is something a little bit tricky. Can you explain what do you understand by dissipation? If you could explain it by means of an example or something like that, it would be pretty much appreciated.
Yeah, this is a good point. So it's a good question. More like in a generic sense, the geometric objects that I obtain from these equations, when I compute their divergence, so imagine I have what we will be the Hamiltonian forms. If I compute a divergence of a Hamiltonian form that satisfies this equation, this will no longer be conserved. This will no longer be zero. That is the case in the multisymplectic setting. However, now this will be minus this part exterior product with my differential form. In this sense, it is dissipative in the sense that its exterior differential satisfies well, partial differential equations which resemble the usual equations that satisfy a particular function. So on the case of contact mechanics, so the difference, the time derivative of my function is minus the rep applied to the Hamiltonian times my function. And this is measures that, well, these functions are not conserved. These functions are dissipative with time. And this is more generally what...
Okay, because you know, in ordinary differential equations, what you mean by conservation normally is that there is one function that is conserved. Normally in symplectic geometry is the Hamiltonian. When it's not preserved, you can say about dissipation, different types of dissipation. But when you have field theories, you have sections, you have mappings that are on a certain manifold, yeah. So talking about conserved quantities is more tricky. Normally, there are things defined integrals over a space, or it can be as a function or whatever. So that's why I ask. And it's something that to apply this to particular example if this is interesting. So thank you for the
Javi,
explanation. Yeah.
It's a paper when we consider a lot of examples with
Okay.
dissipation. And on the other hand, this is not a general dissipation. This is like in mechanics. It's a dissipation according to a rate of dissipation given by the Hamiltonian.
Okay, I understand.
Not dissipation in general.
Yeah, thank you, because you know, Manolo, everyone has his own definition, his own meaning, and when one tries to apply it to certain example, it's important to know what you are doing. Thank you.
And in this paper that mentioned Rubén is a practical. This is just for physics. This is just contain a lot of things.
Great, cool to know. Thank you, really appreciate it.
So this is the paper Manolo was talking about, just to reiterate. Okay, good. So now I'm going to start about the work we did, which is again I'm going to forget about all of this this particular structure of the form. And sorry, did I miss it? So this particular structure of the form, now I'm going to have a more general form. But first I need to define some geometric tools that I will need. And the first one is the Southern Nine-Huish bracket, which is defined as follows, or can be defined as follows. So I will denote by mathfrak x, let's say, super P, the space of all multivector fields, P multivector fields. So there is the Southern Nine-Huish bracket is defined as the unique bracket that takes a P vector field, a Q vector field, and gives me a P plus Q minus 1 vector field, such that it extends the Lie bracket of vector fields, the usual one, and in such a way that it defines a graded Lie bracket under a certain degree shift, but also satisfies a graded Leibniz identity with respect to the wedge product. In fact, this second property is enough to get the uniqueness, and then you obtain the first one, you can prove it. And this is called the Southern Nine-Huish bracket, and this is something I'm going to need a lot during the talk.
Rubén, if you allow, don't take it bad, but there is just one extension, and it gives an Gerstenhaber algebra structure. But just telling, in the literature, there are many things called a Schouten-Nijenjic bracket, lots of them, with different conventions. So it's a little bit tricky.
Okay, yeah. I mean, the signs convention are a little bit.
I mean, in every time you work with something graded, there's always a choice of these sign conventions.
Yeah, there is one manner of doing it in a unique manner with an algebra and Gersten-Haber algebra structure. But South Indian bracket in literature, there are lots of with different conventions. And the worst thing is that different works at different steps, they may mix them using things for one. So it's kind of tricky. Just that it was for me a mess sometimes to do with it. It's just a comment in general. It can be interesting. Thank you.
Yeah. It's true. Thanks for the comment. I usually work with the signs. Well, there are lots of them, as you said, but usually with the one that make this a Gersten-Haber algebra, as you said. More particularly with the ones on the Marley article. I do not recall exactly. Well, but yes, there are a lot of sign conventions. But I fix one of them and I work with these ones. Great. Okay. So now I will take a smooth manifold and a particular differential form, and I want to study what are its conformal symmetries, the conformal symmetries of the differential form. The definition is clear for the case of vector fields, but I want a more graded definition, so a version for multi-vector fields. And well, this was the first problem that we came with when we were dealing with the problem of defining graded Jacobi brackets. And eventually we came up with the definition. I'm going to motivate it later. But this is just a purely functional, say, computational definition in the sense that if you define it this way, everything works. And then I'm going to try to justify why it works if you define it this way. So it's going to be, I say that a multivector field U defines an infinitesimal conformal transformation if there exists a different multivector field of 1 degree less, which I call the conformal factor, in such a way that the Lie derivative of the multivector field of the form, with respect to the multivector field, which can be written as this graded commutator, is precisely the contraction of the conformal factor on the theta. I will denote by this the space of conformal transformations. And notice that these definitions recover the usual definition of conformal transformation or conformal symmetry, when X is a vector field, so I have a vector field rather than a multivector field, as V, because of degree considerations, would be just a function instead of a multivector field. Okay, so as I said, we initiated the study of these multivector fields more from a computational point of view. So rather after trying a lot of definition, this is the one that finally we came up with and the one that it works. But recent considerations have made for us to try to justify this definition. And this is what I will try to do now. So from the more non-cooriented point of view, say, when I have a differential form of higher degree, it not only makes sense to consider its first kernel, but to go, say, on a more graded version, right? So I have the vector fields that annihilate this form when contrasted with it, the 2 vector fields that annihilate this form when contrasted with it, etc. The 3 vector fields, 4 vector field, 5 vector field, up until, well, the degree of the form. Otherwise, I get every possible element. Great. So, and I say, in the more, this generalizes the notion of, in the contact setting, that a multivector field is an infinitesimal conformal transformation of this particular family of subspaces, if and only if the bracket against any possible multivector field taking values in this space lives again in this space, right? So equivalently, it defines a graded derivation. This is a module. This is a module, and this would be a graded derivation of the module. Great. And this definition is equivalent to the one I presented before, right? And the computation I'm just going to show, it's straightforward if you use the Cartan calculus, say, of multivector fields with a fixed sign convention, which is really just if I know that this holds for every, sorry, this would be a W. If I know that this holds for every possible multivector field, then this holds for every possible multivector field for every U, and then I make a few changes. So I make commutators. I express the contraction by the shouted line hoist as the commutator of the Lie derivative with the contraction, and then I write that this should be 0 for every W, right? So I have a particular differential form, so the Lie derivative of theta with respect to u, in such a way that the contraction with this multivector field, any multivector field W, that takes values in the kernel, it's actually 0. And it's an exercise of multilinear algebra to show that this implies that this form is actually the contraction of some multivector field with my form. So then I recover the one previously, and the other implication is very much straightforward. Great.
Rubén, one question. Can you do this the other way around? I mean, you pick up something that it belongs to the lambda n or whatever, some subset, and then you require it to be described by means of a theta form. So, could you describe the existence of theta in this manner? I mean, put the slide before this, please. One moment.
Yes.
Imagine that you have something, okay, that belongs to lambda PTM. Yeah?
Okay.
And now I ask you, can you describe the kernel of a theta? Can you give me a description?
Okay, and I see. So you start with a family of subbundles. I don't know if you start with a family of subbundles, and then you wonder whether this actually arises as the kernel of a theta. Is this the question?
Yeah, this is the question.
Okay, I see. Of course, not every possible subbundle arises as such.
Yeah, of course.
One condition sufficient and necessary, at least point-wise, right? Theta would not be unique.
Yeah, sure.
It's that this should be a module with respect to the wedge product of vector fields, and also on the top level, so on the with p equals to n, say, it should be of codimension 1.
Yeah.
Then you can guarantee the existence of the theta point-wise, say, and not even would not be unique either.
Yeah, sure. Thank you.
No, thanks for the question again. Okay, so again, denoting by mathfrak h the space of conformal infinitesimal transformations, we have two properties which are very important, which is that it is closed under some nine-hoist bracket, and it is closed under the wedge product. The first one should be maybe obvious, and the second one, for at least for us, I think was a little bit more surprising. This is certainly not the case in the case of multisymplectic theories, but once you allow for a conformal symmetries, it is satisfied. So in particular, it closes against Haber algebra, subalgebra really, and the proof is just again using the Cartan calculus, the thing that I did before, just apply several different commutators, and you obtain these two properties. Great. So, in order to motivate the definition of the brackets, I'm going to make an analogy with the contact case, co-oriented contact. I will say a little bit more on the non-co-oriented version later. But if I have a contact manifold, I know that for every two functions on my, sorry, this would be a space. For every two function of my manifold, there are unique vector fields, which are conformal, right? So they define a conformal infinitesimal transformation of the eta, and in such a way that they satisfy this. So the evaluation of the eta on the first vector field is minus the f, and the other way with the g. And then I can define the Jacobi bracket as the function associated with the Lie bracket, right? So I get, there are other possible definitions for this with different sign convention also. But so in this way, I obtain that the Hamiltonian vector field of the bracket is the Lie bracket of the conformal vector fields immediately. Okay. So when the structure is not cooriented, instead of functions, which are really sections of this trivial bundle, we have a similar correspondence, but rather with sections of the line bundle, which is the annihilator of the annihilator of the kernel of eta, right? So the annihilator of the distributions. And we will use this principle, so this principle in contact geometry to define a correspondence, which will be of conformal Hamiltonian forms, I will define it now, and conformal infinitesimal transformations. This is the definition. Okay, so I have theta to be an arbitrary differential form, and I say that an A form is a conformal Hamiltonian form if it's the contraction or minus the contraction on theta by some infinitesimal conformal transformation. So this, remember, it's a multivector field such that it's the Lie derivative of the theta with respect to the multivector field is some contraction of some conformal factor. And as usual, I will denote the space of conformal Hamiltonian forms by omega sub h. Great. And then I would like to define the graded Jacobi bracket as minus the contraction of the Schouten-Nyquist bracket of my conformal transformations. So, of course, some compromisations are in order. First, this multivector field is not necessarily unique, so I need to guarantee that this actually is well defined. And it is. And again, it's just using Cartan calculus, which I'm going to show because I think this is an important point, that the Jacobi bracket is well defined, which is just done as follows. First, I write the contraction of with the Schouten-Nyquist bracket using the commutator with the Lie derivative and the contraction. Then this Lie derivative, because X alpha is a conformal symmetry, it's actually the contraction with some V alpha, and then it's already done, right? Because I can pass this V alpha the other way, paying some sign, and then I get some operation on the contraction of X beta and theta, which is precisely minus. So maybe here I'm missing a minus, but minus something I do on beta. So it actually only depends on beta and the vector fields associated to alpha. But then, since all of this is graded skew-symmetric, the same holds for alpha, right? So the bracket only depends on alpha and beta and not the choices that I make on the multivector fields. Great. Okay, so now what we have really proved is that under contraction, right? So I have here the space of multivector fields, conformal multivector fields. I have here the space of Hamiltonian forms, and what I have defined, right? What I have proved is that under contraction, I have an induced bracket, right? So the Schouten-Nyquist bracket goes to a new bracket, which we call the graded Jacobi bracket. And we can also do the same for the wedge product, right? So instead of the same diagram, but instead of writing here the Schouten-Nyquist bracket, I write the wedge product. Since I know conformal transformation, and close under wedge product. And here I obtain a new product, a product of conformal Hamiltonian forms, which I denote like the V, and it's called the cap product. Right, so from the Gerstenhaber algebra structure of conformal Hamiltonian multivector fields, I obtain a Gerstenhaber algebra structure on forms. Okay, and this is this slide, right? So this particular algebra with this bracket and this product, cap product, satisfies the axioms of Gerstenhaber algebra. Also, I have added this one just to make it as a similarity with contact geometry. This is a weak Leibniz identity, and this other thing is what make this algebra a Gerstenhaber algebra. Great. I should mention this 3 point. This is not present in contact geometry. Not present in contact geometry just because it's trivially zero. So if I have two functions, I have their associated Hamiltonian vector fields. If I make the wedge product of these Hamiltonian vector fields, I get a two-vector field that when contracted with my one form, it's zero. So this does not appear in contact, but it does appear when I take into consideration differential forms of higher degree. Okay, so just to mention, you can do all of this from a non-covariant point of view, say. So instead of a differential form, you start with a codimension one multi-distribution, so just a codimensional one subspace of this particular vector bundle. And then you obtain the other multivector, so you obtain the graded algebra as first, in the first case, multivector that annihilate the form, and in the other one, multivectors such that when taking the wedge product with any other multivector lies in this multi-distribution, right? Then infinitesimal conformal transformations of this theta corresponds to derivations of the graded algebra, of the graded module rather. And then the Gerstenhaber algebra of conformal Hamiltonian forms is really the Gerstenhaber algebra of the derivations. And you can actually define So a more explicit description in terms of a particular tensorizing with just the annihilator of this particular distribution. But I'm not going to get into this. But this is a more say non-coordinated point of view.
Indeed, Rubén, this is what I was thinking before when I asked about the theta, because some of these things seems to be independent of the theta form.
Yeah, exactly. I mean, yes, precisely. All of this is actually dependent only on the distribution, right? Not on the theta.
Yeah, that's the main point. And yeah, sure.
Exactly. So very much on point previously.
But it necessarily has to be what you call a multi-distribution on this wedge product, right? It can. Have you thought about distributions of corank greater than one? And
very good question. And ties very well with the examples that I wanted to show.
Okay, thanks.
It did. I was thinking of that too, and I thought that maybe I could tell you something about that.
Yeah. No, then I set up very well the example then. So some examples of these multi-distributions that you can get is, as Xavier asked, maybe thinking in this sense, that if you get an n-codimensional distribution on a manifold, right? So this is more multi-contact a la Vitagliano, say. Then I get a one-codimensional multi-distribution just by making a wedge product with every other element, right? With in order to complement the original one. The fact that this is n-codimensional is reflected in the fact that this is one codimensional, okay? And it's just really a simple linear algebra computation. And then in the more k-contacty flavor, if this distribution arises as the intersection of some kernels of linearly independent one-forms, I can define the theta as the wedge product of this, right? I should mention, of course, no integrability appears here yet. And although from this point of view, you do recover the distribution, from this point of view, you don't recover the forms. Okay, so this is more of like a from an injective, say, from multi-contact a la Vitagliano, you can get the codimensional one distribution, but from k-contact, you do get the multi-contact version, but not the other way around. You cannot go back. Okay.
By the way,
yeah.
Rubén, just a stupid remark, yes, for Spanish people.
Yeah.
It is written and codimensional.
N, claro, of course.
Yeah, because
True.
I say because when I am a referee, I straightforwardly know who is writing this, and this is something for people from Spain is a typical mistake, even for all people or experienced researchers, that no matter if they know or they don't know, they write it is not. Yes, more thing. Vitagliano did it with distribution rather than with forms. There was something like a non-degeneracy of a certain map. Yeah.
Yes. Oh. I will get into this later. Yes.
Okay. Thank you.
By the way, I see I have already eaten up like 40 minutes, which okay. Oh, and then you can do active-independent fields, which is just with this particular form. You can do all of this stuff. In any example that you get a form, you can do all of this. But in these particular examples, when you get the integrability conditions or non-integrability conditions that Javi and Xavier were talking about, you will get the multi-contact as I will define in some moments. Okay. So these are some references for it. So the article by Luca Vitagliano, of course, the article by Javi, Xavi, and Thomas on k-contact geometry, and then for the multi-contact field theory, just see the previous references. Okay. So as a conclusions of this particular section, I want to remark that if you have an arbitrary differential form, you may study its conformal transformation in a graded sense, right? And these conformal transformations are closed both for the Schouten-Nyquist bracket and the wedge product. So by dualizing, right, contracting by theta, you can get an induced structure of subclasses of differential forms, which we call conformal Hamiltonian. And this structure is really a generalization of the usual Jacobi bracket, but to a graded version, right? And it recovers a Gerstenhaber algebra. Good. Okay, so now I want to get into the theory of pre-multisymplectizations and multi-contact structures. And first I want to do some motivation. Well, first some definitions and then a motivation. This probably everyone knows, but still. So what is a pre-multisymplectic manifold? Just a manifold together with a closed form, closed n+1 form, following the end that I will get here. And it is called multisymplectic or non-degenerate if the map defined by contraction is a monomorphism, right? I get this. This is the definition. I have here as well a notion of not conformal but Hamiltonian form, which is a differential form. It's called Hamiltonian if it's exterior differential. Here I'm missing a tilde, sorry. If it's exterior differential, it's a contraction with some multivector field on my particular differential form. And then I get a graded Poisson bracket. Again, I'm missing here tildes, which is, or rather, maybe I should remove this one, but it's okay. There is a graded Poisson bracket, which is defined as follows. And this sign convention is, this sign is used for obtaining nice formulas. Good. So just a few remarks on these brackets, like a particular but non-defining property, right? So this is not enough to record the brackets, is that they satisfy a Jacobi identity up to an exact term. So in particular, when I restrict these brackets to n-1 form, I recover what people refer to as an L-infinity algebra, right? However, just to mention it, these brackets satisfy a lot of more interested properties. One takes into account the graded nature of the bracket, and just to do some publicity, I will put this article here. But I will use this L-infinity algebra stuff to, well, at least mention when I talk about the correspondence of the brackets, the graded Jacobi and the graded Poisson brackets under the process of pre-multisymplectization. Great. So now, what is symplectization? Well, symplectization is a procedure that assigns to a particular contact manifold. It can be really contact distribution, but I will just, for simplicity, work with co-oriented, which assigns to a particular contact manifold a symplectic manifold, which is called its symplectization. And it's just I multiply by the real line without the zero, and then I define this particular structure. So omega is the minus differential of this form, right? So it is a one homogeneous symplectic manifold. And this defines a correspondence on equivalence of categories of contact manifolds with homogeneous symplectic manifolds. And this can be used to try to solve problems, right, in the contact realm to go to the homogeneous symplectic realm, or vice versa, right? And this is what we want. We want this correspondence. So also more generally, this can be understood as if I get a codimension 1 distribution, I have a homogeneous presymplectic. When I restrict to contact, I get homogeneous symplectic, right? And we want to have the similar picture for multi-distributions or for differential forms. And this is what I will refer to as pre-multisymplectization. And we will benefit in this talk, if time allows. We will benefit from this procedure because, well, I can use a lot of the information from the brackets, which we know, right? We have a lot of information from the multisymplectic side of the brackets on the multisymplectic side to obtain information in the brackets of the multi-contact side. Which this will be used later to prove that certain thing closes an algebra. Great. Okay, so then let me get into definition. A differential form, n differential form, so fixed, sorry, a differential form, or more generally a one-dimensional multi-distribution. And I define its pre-multisymplectization to be exactly the same manifold. So I take the manifold, multiply by the real line, except the zero, and together with the form n+1 form, which is the minus exterior differential of this form, right? Of Z, which is the coordinate on R, times theta. This makes this manifold into a homogeneous pre-multisymplectic manifold. We can define more general pre-multisymplectizations. So there should exist a conformal factor, and there should exist a particular vector field, such as several things hold up. But well, more or less these are all the same, up to a universal cover, up to a, well, covering in general, up to a covering of my manifold, or pre-multisymplectizations coincide, more like coincide in a neighborhood or something like that. Okay. But I don't want to get into this. Okay, in the case of a multi-distribution, what we do? Well, we simply consider the line bundle of the annihilator, just as in the contact case. This canonically embeds in the bundle of forms and hence has an induced pre-multisymplectic structure. Of course, these two coincide once I trivialize this line bundle or locally trivialize this line bundle, if trivializable, and these are exactly the same. Good. Okay.
Sorry,
So-
a silly question. Can you
Yeah.
repeat why the annihilator is a line bundle and not a vector bundle of arbitrary rank?
Yeah, no, this is because this is precisely a one codimensional subbundle.
Ah, okay, yeah, because I had I guess for codimension greater than 1, this procedure doesn't work as
Yeah,
easily, right?
maybe what you can do is take a wedge product with vector fields.
Yeah, because as far as I know, well, thinking in the more general procedure, in the non-covariant, if you will, as far as I know, an essential ingredient is the fact that there's a canonical one-to-one correspondence between line bundles and principal bundles with principal group, well, the multiplicative group of real numbers, or if you want, GL1, whereas for GLN, there's not a canonical action of GLN on a vector bundle of, so for rank greater than 1, this procedure is...
Xavier, we thought of it with Thomas and with Xavier. We even thought how to generalize in certain cases and how to solve it. The only thing is that the structure is a little bit more complicated. The linear case is very easy. Even if you have no theta, whatever, you can describe it in a nice manner. But when the corank is larger, you fall into all the structure. It's not a principal bundle anymore. There is a no canonical way. There are other structures that can be described. We can talk one day if you want to.
Okay, thanks.
But yeah, if this is, as you said, maybe higher codimensional, maybe what you can do is try to build, as in the case of distributions, right? A one codimensional subbundle of maybe higher multivectors, right? Or something like this. And then apply the same procedure, but of course, not with a fixed index. But I really have not looked into this. But
Thanks,
it is an
Rubén.
interesting point.
Thank you.
No, thanks for the questions. Okay, so then let's start studying the conformal homogeneous correspondence from this graded new point of view. So if I have a particular differential form, what we proved is that for any infinitesimal conformal transformation, any multivector field, there exists a unique up to the kernel, right? This is something that you work with just in this sort of geometries. There exists an up to kerp, a unique multivector field, which we denote by tilde u, that satisfies two things. The first one is that it's Hamiltonian, right? So the differential of the contraction of omega is equal to 0, or the Lie derivative, the graded Lie derivative with respect to u tilde of omega is equal to 0, and it projects onto u the original vector field, multivector field, under the canonical projection. This is just this multivector field is called the lift. In the case of the trivial, on the canonical multisymplectization, this is just constructive, right? I can just define it as such, and then prove that it's unique. But for more general multisymplectization, it needs a little bit of work, not a lot, but some work it does need. Okay, so I can lift multivector fields, conformal multivector fields to Hamiltonian multivector fields. Okay. So if I can lift multivector fields, I can also lift the correspondence form. So I have the conformal Hamiltonian form on the base, and I can lift it to a Hamiltonian form on the top, right? So if I have a particular conformal Hamiltonian form for a differential form theta, then its homogenization, which just multiply by set, it's a Hamiltonian form on the pre-multisymplectization, and we recover the bracket as such. Maybe this is a bit surprising. You don't recover the precise exact bracket, but this really makes a lot of sense why you get the exact term here. So what you obtain is that the bracket of the homogenization is the homogeneity of the bracket plus certain exact term, which involves the cap product. And really, you should recover something of this sort, because the graded Poisson bracket satisfies the Jacobi identity up to an exact term, but the graded Jacobi bracket satisfies the Jacobi identity exactly. So either you get this modification or something weird is going on. But we do get it. So this is good. And well, in the non-oriented point of view, we can simply tensorize by this annihilator and exactly the same correspondence holds. Great. Good. Okay. So as I said before, we don't get an exact correspondence, but what we can prove is that with these morphisms, this formula defines, well, says to me that the process of homogenization defines an L-infinity algebra isomorphism, right? So this is referred usually to as the Lie algebra is a realization of the L-infinity algebra, right? So I have accidentally added exact terms, and I can remove them by certain isomorphism. This is in fact a generalization of a correspondence defined by Luca-Vitriagleno, which for n-dimensional distributions to general multi-distributions, right? So you obtain the previous case from this one just by taking the exterior product with n-1 vector fields. Okay, I see I have 10 minutes left. So once this is said, I have the process of pre-multisymplectization. When do I say that a form is multicontact? Well, I say that it's multicontact when its pre-multisymplectization is a multisymplectization. This is a bit of a circular definition, but I think, motivate it, relating back to a condition on theta or more generally on the distribution, right? So the following two statements are equivalent to a form being multicontact. The first one is that the intersection of the kernels is trivial, right? The kernel of the theta and the kernel of the differential of theta should be, the intersection should be 0. And also the theta is not in the image of the bundle map, which comes from the kernel of theta to the n-1 form, and it's just, sorry, this would be n forms, not n-1. And it's contracting against the exterior difference. And also, more in the usual contact sense, that the pairing that takes vectors to multivectors modulo multivectors in the kernel, that is evaluating the Schouten 9 bracket, is non-degenerate. This pairing is non-degenerate. So these two conditions are equivalent to the pre-multisymplectization being actually a multisymplectization. Great. Okay, so what do we obtain? Since, well, just previous observations, since multicontact forms are invariant on the conformal transformations, multicontact forms are invariant on the conformal transformations just because ultimately it's a condition of the graded algebra, which is the kernel. Right? And we get this equivalent. So codimensional one distributions correspond to homogeneous pre-multisymplectic, and multicontact corresponds to homogeneous multisymplectic. Just this was defined ad hoc, say, but then I think it is sort of justified once we prove that these two conditions are equivalent. Great. Okay, coming back to the examples, right, the ones that Javier and Xavier mentioned. If I have a core-rank n usual distribution, right, so just vector fields, core-rank n, and this is if it's maximally non-integrable if and only if the multi-distribution built as such is multicontact. And equivalently, this distribution is maximally non-integrable if and only if this form is multicontact.
Sorry, Ruben, can you remind what do you mean by maximally non-integrable? Because there are several definitions, they are not
okay, yes.
equivalent.
I mean that the curvature form, so the map, the skew-symmetric map from D to the tangents divided by D, it's non-degenerate pairing. This is what I mean. Maybe I should have defined it. I wasn't aware that there were several notions.
No, never mind. This is not a distributional matter, but they are forms, and everyone says a different thing.
Yeah,
I mean, there are some main, how to say, some of the definitions they are more extended than others. Yeah, but there are several ways of understanding it.
Okay. Thanks for the point. Okay. In the more field theoretic side, these forms are multicontact. Okay. This form is almost trivially multicontact. Trivially, I mean that just do the computations, which are very simple. This is not so trivially multicontact, but at least when you fix the dimension to be greater or equal than 2, it is, right? Why this fixation of n greater or equal than 2? Well, first of all, if you get exactly n equal to 1, this is even dimensional, so this should not be compact, right? But for fields, this is multicontact. for any function, for any possible Hamiltonian.
And Rubén, sorry, do you have any canonical example? I mean, some Darboux theorem, something that allows you to say that every example is more or less locally of a certain type, or a certain class of types, or something of this sort of.
Yeah, I mean, this goes just as in the multisymplectic side, right? If you impose enough conditions on a differential form, you eventually get a Darboux theorem. And
Okay. But there are many Manus, yeah?
Yes, exactly. Exactly. Precisely. Now, I mean, in the original works, so the ones that I mentioned before, they proved the Darboux theorem for these sort of structures, right? So if I have a form which takes this particular linear type and it satisfies certain conditions, locally it looks exactly like this, right? But then, of course, in general, it's something that it's almost impossible. No, it's
there are too many examples there to give a classification of canonical form. This is normally with these things you ask for a polarization or something like that. It's
exactly.
interesting to know if there is something like that in this case.
Yes, exactly. So this is the same thing that happens in the case of closed forms in general will happen here as well. Okay, so conclusions of this particular section again. The pre-multisymplectization procedure, what it does is just defines a correspondence between conformal objects on my manifold together with a differential form or a multi-distribution, one codimensional multi-distribution, and homogeneous objects on a certain pre-multisymplectic manifold. We may lift conformal multivectors, which they also lift, they induce a lifting of conformal Hamiltonian forms, and we have that the brackets are related up to an exact term, right? This is what I mentioned. You get you get a realization of the infinity algebra as a Lie algebra. And finally, this correspondence induces the notion of multicontact geometry, which generalizes a notion present in the literature, at least the one of multicontact by Vitagliani, right? As I mentioned before, from K1, so a family of K1 forms, you do obtain multicontact, but then you don't recover the K1 form, right? So if you want to work with the K1 forms, maybe this is not a thing to do. Great. So I have 2 minutes left, and I'm missing a whole section.
Rubén, don't worry, you can speak a little bit longer, okay? It doesn't.
Okay.
10 minutes is okay. It's not a problem. Yeah.
Okay.
Indeed, all the questions I have now to make you, they are rather about dynamics, having to do on the value questions, manifold Lagrangian relations to. So please go on. Doesn't matter.
Perfect. And then I will go on a bit longer, maybe 10 minutes or something like that. Thanks. Good. So then I want to define dynamics in this more general setting, try to define the dissipation form in this general setting, and also mention something of dissipated forms. Okay. So I start with a multi-contact structure. At least the way that I like to think about this is, I mean, if I want dynamics, I need to have a fibered structure over certain manifold, which will be my spacetime usually, whose sections will be just the things that the solutions of the certain PDF that I'm looking forward to. Okay, so we will assume certain compatibility, and the certain compatibility that this projection has to be at least one vertical. So, sorry, not the projection, but the form needs to be at least one vertical, meaning that when I write it locally, it has all of the x's plus maybe one dy or one dp, whatever. So, for instance, in this particular sense, this form is one vertical because the differential of vertical coordinates only appear once, but not more. Okay. So then I can define the rep distribution, which is those vector fields that when contracted with the differential yield something semi-basic, right? And again...
sorry, Rubén.
Yes.
You cannot talk about that, about contractions with vertical multivectors, something like that?
Sorry, say again?
Couldn't you explain that in terms of the contraction with vertical multivectors?
Yes, exactly. Yes. Okay. If you contract with, so this means one vertical means if you contract with two vertical vector fields, you should get 0, right? And this is what this means. Yeah, thanks. So you can define the rep distribution as those vector fields in such a way that the contraction with the stereo differential is semi-basic. So we will assume several things. these two work. Maybe you can then go to the degenerate cases and work further there. But first, we will assume that this is vertical and that it also defines a distribution, right? This word that here I'm cheating a little bit. Great. So just as a disclaimer, this is a little bit more general than the work that we did in the original article, but we have recently noticed that we may extend it as such, and this is the way that I'm going to present it. So in the original article here, you may see a 0, but this kills a lot of cases, so we rather put here semi-basic. Great. Now, I need to define something which will give me the dissipation form, and this will be the rep multivector field, okay? Not a vector field, but a multivector field, and it's defined as follows. And not even a multivector field, I will explain it in a moment. So what I want to do is to study this. I take the rep distribution, and I contract the rep distribution both with the theta and with the differential of theta. So I get a fibered map from this distribution to the bundle of n-1 forms on X and n forms on X. All of this is well defined, right? Since this is vertical, and the form is at least one vertical, this would be semi-basic, and this is semi-basic by definition, okay? This is always injective, so it defines an isomorphism to this image, which I denote by Z, okay? And then I may compute the image of this map with the inverse of this map when restricted to the image, and I get a tensor of this sort, right? I get something that lives in the rep distribution tensor with the dual of this particular space. This dual of the dual of this particular space is just n multivectors plus n-1 multivectors divided by whatever annihilates this. Okay, divided by multivectors that are 0 when contracted with this. Okay, I will make explicit computations now. I think it will make things clear. And then this is a contravariant object. Okay, and this is what I will refer to as the multivector field. Notice here the skepticism. Plus some factors, some numbers which make everything work. Okay, so now I should mention why do we take this direct sum or not other things, or not just this particular thing. Really, the thing that we are looking for is to make the extended formalism and the reduced formalism work together. But also I have some pairings. I have all the things that I do with forms and multivectors, I can do with pairs of forms and pairs of multivectors, right? So I have a certain relative pairing, and also I would have the wedge product, the Lie bracket, the exterior differential, and everything has the same properties. Okay, everything has the same properties. So the rep multivector field is not really a multivector field; it's a relative multivector field up to some kernel, which again really appears. I mean, you have to deal with it. Okay, let's make some computations. So if I take the example of the extended formalism, I take this particular differential form, and I compute its rep distribution. What appears is the partial with respect to the S's and the partial with respect to the P. The isomorphism then reads as follows. The partial with respect to the S goes to the n-1 x mu and 0, and the partial with respect to P goes to 0 minus the nx. Okay, and then the relative multivector field is precisely this thing. Right, so partial with respect to S, tensor, partials with respect to the rest except the x mu, and this thing here with the P. Plus, I need to be careful, here are kernel terms, however, in this case, the kernel terms are trivial. So this is the relative multivector field. Okay. Now I can go to the reduced formalism, and if I take H to be any Hamiltonian, this takes this particular form, and now the rep distribution is what one would want to be the rep distribution, which is really a partial with respect to the S's. And now the isomorphism reads as follows. So the partial with respect to the S mu goes to this plus this new term, right? Plus this new term. So that we get this multivector field, and now I have a kernel, which is this, and I need to be careful about this. I need to be careful. But these two multivector fields are related by the projection, and essentially makes everything works. comparing the extended and the reduced forms. Okay. Now, so I have a relative multivector field, and I told you that making computation with relative stuff is the same as making computation with usual multivector fields and forms. So now I can contract it with the relative pair theta differential of theta. And what do I get? What do I get is the form. If I make this contraction, first I need to be careful that this contraction should be well defined, and it is well defined. And it gives me a number, and it gives me a one form. This number is always 0. And this one form does not need to vanish, but this is the dissipation one form. Okay, this is the intrinsic dissipation one form, we say, in the sense that it does not depend on the Hamiltonian. I have the form, and then I get some dissipative term. In the extended case, it's just 0, but in the reduced case, I get what the usual dissipation form. This is the one that I introduced earlier, although here there was an L instead of an H. Great. Okay. So now I want to do dynamics. I want to do dynamics, and I want to write the equations. So I will say that a Hamiltonian is just a semi-basic form on my manifold, and then I will define the dissipation form of the Hamiltonian by contracting again with my relative multivector field on a certain relative form, which is just the differential of H and 0. And I get this. And plus a sign, plus a factor, this is the dissipation form. In both cases, the extended and the reduced formalism, if I have this particular Hamiltonian, I get this particular dissipation form. And then with this, I can define the equations. But first, I need to define the D-bar operator. So now, if I have a multi-contact manifold, and I have, with the restrictions that I already mentioned, and I have a semi-basic Hamiltonian, I can define this operator, which is the exterior differential, and twist it by making the wedge product with the intrinsic dissipation one form and making the wedge product with the one form associated to the Hamiltonian. And then the Hamiltonian-Underville equations are defined as such. So first, this is usually referred to as the holonomic condition. By taking the pullback of theta, I should get minus h, and by taking the twisted differential of theta plus h and contracting by any vector field, then making the pullback, I should get 0.
Rubén,
yes.
The differential has the properties of a differential?
No, okay, no. This is a good point. Only when these are closed.
Oh, okay. Yeah, that's what I expected.
Well, rather when the sum is closed. When the sum is closed. Yes. No. This I made some abuse of notation here. No, this is not really a differential in the usual sense. Okay. Great. So this is okay. I will. It turns out that the most interesting cases is that those ones with this sum being exact. Well, I mean, or locally being or closed really, but as well as before, you can define correspondence between the solutions of the multi-contact Hamilton-Underville and the Hamilton-Underville equations, just as before. Okay, so if you take the multisymplectization and take the homogeneous Hamiltonian, which is just this is just a typo. So it's set times no, not a typo. I'm missing an equal here. So the tilde h is set times the previous h. Then I have a correspondence. Any solution of the multi-contact can be lifted to any solution of the Hamilton-Underville equations, and any solution of the Hamilton-Underville equation projects down to a solution of the Hamilton. The conditions here on being exact is really a topological condition on being able to lift. You can always locally lift. Right? The condition of being exact is telling that you can globally lift. Okay. And furthermore, if alpha is a conformal Hamiltonian formula for the evolution. So the exterior differential, evaluating the exterior differential on solutions of the homogenization is exactly making this operation. So taking really the twisted differential of my form via the contact in the contact world, in the multi-contact world. Great. This can be used to define what I will say now. But first, notice that this implies a correspondence between closed forms on the multisymplectic side and dissipated forms in the multi-contact side, in the sense of this article, which is by Xavier, Narciso, and Bartos, which is the form is said to be dissipated if these equations. Sorry, I'm missing here an exterior differential. If these equations hold. And then what we have just showed is just dissipated forms correspond to closed forms on solutions via the process of multisymplectization. And we may use this, finish now, and we may use this to prove using some result that Manuel and I have on the case of multisymplectic side. That is that the graded family of closed forms and solutions is really a graded subalgebra under the graded Poisson bracket. This is very much not trivial, or at least it was not trivial to me. The case of n-1 forms, it is trivial, but when you go to the graded side, everything gets complicated. But since we already have the work here, right? Since we already have the work in the multisymplectic side, we might as well, via the process of multisymplectization, obtain a theorem in the case of multicontact. And the theorem would be like, when the dissipation form is closed, not necessarily exact, when the dissipation form is closed, dissipated forms of any degree close a graded algebra under the graded, Jacobi bracket, not Poisson, Jacobi bracket. This is what I wanted to mention. I'm going to finish now. So just add some conclusions. So what we have given is a more general treatment of multi-contact structure that I've tried to show you that can be seen both from the co-oriented and non-co-oriented point of view. In this general picture, we can introduce the graded bracketed forms, right, which is a generalization of the Jacobi bracket. We can write the equations in a more flexible setting. In particular, what I think is clarify some definitions of the dissipation form. Maybe you don't agree with this, but this is at least a more general point of view, and I like the contracting with a multi-vector field, and that's it. And also, like together with the process of multisymplectization, we can prove that the graded dissipation laws are closed under the graded Jacobi bracket. Great. So some further work that I think would be very interesting to see is that to prove a graded nether theorem, so generalize the work by Narciso, Xavier, and Bartos to a graded version. Also find, to allow for more flexibility, to find the notions of graded Jacobi structures, right? Multisymplectic structures cannot be quotiented, at least not now. But if you quotient a multisymplectic structure, you get a graded Poisson. So maybe these sort of the things are true as well in the multi-contact realm, just adding instead of Poisson Jacobi. And on the more geometric side, we don't have yet the complements of coisotropic, Legendrian, etc. So we don't know yet what are these notions, but this is also work that would be interesting, right, in the more purely geometric setting. Okay. For the references, this is just the ones that have been appearing on the talk, and that's it. I will finish now. Thanks for the extra 13 minutes now. Thanks for your attention.
Thank you very much, Rubén. It's been a real pleasure. Okay, any question? Remark?
Yeah, could you come back to this definition of something is multi-contact when there is a multisymplectization?
This one, no?
Yeah, the next slide maybe better. Yeah, I was thinking if this could be generalized. In the case of one forms, you can define what is called the class of a one form. So the minimal class is when you have a closed one form, and the maximal class is when you have a contact form. So the class measures the integrability or non-integrability of the distribution generated by the one form. So maybe here, because could you go to the previous slide?
Yes.
Yeah, exactly. So if you, instead of non-degeneracy in the second condition of the proposition, impose something about the rank or something, maybe.
So you are thinking more of like getting a correspondence between, say, fixed rank, so distributions where this has a particular rank, and pre-multisymplectic manifolds of certain type?
Yeah.
I don't know.
Yeah,
Maybe.
or co-dimension one distribution of a
Yeah,
certain,
I see.
Because, well, I mean, as far as I know, this notion of class for one forms, or sometimes called Fathian forms, was introduced to study certain systems of differential equations, because this measures how much can you integrate them, let's say. So maybe this for when instead of a one form you have a K form, you think
Maybe.
of a similar notion.
I couldn't say it right now, but maybe. If it could be done, I'm sure it would be complicated because the
Yeah, I mean, for sure.
multilinear algebra is not something to mess with.
Absolutely.
But yeah,
Come on, but it is fun.
yeah, it is fun. It is fun. No, but I think it will be interesting. Yeah, maybe you could do a generalization.
Okay, any other question, remark? Well, I have lots of, but I don't want to take this too long, this too long. Just tell him that I was thinking about several questions, but at the very end, you describe more or less all of them in the last slide in the work to be done.
Okay.
Indeed, I was mainly thinking about Legendrian submanifolds in this context for the dynamical systems. About the things Xavier was talking about, I was also thinking about how to do this with distributions. So if you have any idea, it would be nice. And also I wanted to ask you how to generalize the work by Bartos with Narciso and Xavi. But okay, let us say when you will have something, let us know. It would be cool to know about it.
Yeah. I really cannot say anything of the last point. I'm sorry to disappoint. But maybe I do have something to say of the graded nether theorem. This is at least a work in progress in the multisymplectic setting. We are working on it. Then via the process of the multisymplectization, right, you would obtain a nether theorem in the multicontact.
And a reduction, but this is too far away from.
Reductions are, of course, very interesting. But this, I think, would benefit more from the Jacobi point of view. A la Marsden-Weisstein reduction, I'm not sure. Maybe you can do things, but I don't know. Seems difficult.
Okay, one day, let us say, when you have more, we will hear it very kindly. Yes, one thing, it could have been cool, at least for me, and I guess for many more people, to have just an example of all these things. Indeed, I will tell you about the dissipation, that there are very nice works, geometric nice works, and there are many nice people working on PDEs and conservation laws and things of the sort. And sometimes things we do, they can be applied to their examples, yeah? And sometimes they don't know that our techniques can be used for their problems. So even in the easiest case, I find quite interesting to describe what dissipation means. But I mean, it's a simple example, yeah? But this is just I don't know, more or less personal comment about what can be done. That's just a thing.
I mean, as Manuel said, there are a lot of examples. I mean, in the case of the more maybe canonical, or the way that I like the most maybe is that the electromagnetism on media. I would have liked to maybe do a full work here of a particular Lagrangian or this sort of stuff, but I already went late with my slides, so maybe it would have been a little bit more difficult. But
sure.
Definitely the example, like doing the detailed work on this sort of graded stuff in the examples is important.
I tell you because it's been a long time that I see talks by people working on, I mean, in an analytic manner with PDEs, with particular examples doing stuff. I say, come on, this was done even for Manolo, by Xavier, or whoever. And I think that sometimes showing as a typical tracing example, it could be quite interesting. But it's just a personal view. Anyhow.
Yes.
Is there any other question?
Oops.
No. So thank you, Rubén, again for your talk. It's been a pleasure. Please send me the slides and see you in a week with Casey Pleca.
Thank you for having me.
Okay. Thank you. See you all, guys. Thank you.
See you.